Way 62 continues our discussion of math of chemistry by applying the conservation of mass law. Conservation of mass law states that the mass before an equation must equal the mass after a chemical equation, and this shows that the mass is conserved. Another way to apply this exact same law is by balanced atoms. If conservation of mass is to be maintained, then that means that the number of each atom present on the left side must equal the number of atoms present on the right side for each type. So let's try some problems that deal with applying this law. Which equation shows conservation of mass and energy for a reaction at 101.3 kilopascals and 298 Kelvin? So again, for problems like this, you need to consult the number of atoms of hydrogen on the left and right side, as well as the number of atoms of oxygen in order for conservation of mass. In order to show conservation of mass, the number of hydrogens must equal the number of hydrogens on the left must equal the number of hydrogens on the right. So you should be able to eliminate answer choices 3 and 4. Now you notice that 1 and 2 show balanced atoms of hydrogen as well as oxygen. There's 4 on the right of hydrogen and 4 on the left. 2 oxygens on the left, 2 on the right because of that coefficient modifying that oxygen to make 2 oxygens. Now, which of these energies is correct? Well, in order to calculate the energy or the energy of a particular reaction, you'll need to consult Table I. And Table I tells you the heats of reaction for various chemical equations, and the one that's listed shows H2 gas plus O2 gas gives you H2O gas, which is this right here. And that corresponds to a negative 483.6 heat of reaction. Now this is your heat of reaction, and it tells you that negative, a minus sign indicates that the reaction is exothermic. So the energy would be present on the right side of the arrow because it's produced. Energy is being released. So answer choice 1 is correct. Now notice that this is one of the rare occasions where Table I gets used in order to consult exactly how much energy gets either released or absorbed for a particular chemical reaction. So choice 1 is correct. When a sample of calcium solid loses 1 mole of electrons in a reaction with a sample of O2 gas, the oxygen If calcium is reacting with oxygen and it loses 1 mole of electrons, well, in order for mass to be conserved, those mole of electrons can't simply disappear. They must react with the other reactant present in the chemical equation. So if calcium is losing 1 mole of electrons, those must go toward oxygen and must be gained in order for mass to be conserved in this chemical reaction. Otherwise, mass would not be conserved. So answer choice 3 is correct. In a laboratory investigation, a solution that contains 13.2 grams of lead 2 nitrate reacts completely with a solution that contains 12 grams of sodium iodide, producing 18.4 grams of lead 2 iodide, and an undetermined mass of a second product of sodium nitrate. This reaction is represented by the balanced equation below. Lead 2 nitrate plus sodium iodide yields lead 2 iodide plus 2 sodium nitrate. Determine the mass of sodium nitrate produced. Well, in order for conservation of mass to apply to this equation, the mass going in should equal the mass going out. So what's going in? Well, if 13.2 grams of lead 2 nitrate and 12 grams of sodium iodide are reacting, that means the mass of the reactants is 25.2 on the left. So how much product should we produce? Well, we should produce equal masses of product, but it doesn't tell you how much sodium nitrate is being used. So we're going to call that X, and we know that 18.4 plus X grams of sodium nitrate has to equal 25.2 grams of reactant, which is what we started with. Subtracting the values will yield that 6.8 grams of sodium nitrate must be produced. Otherwise, we're not conserving mass here. Therefore, the correct answer is 6.8 grams. Mass going in should equal the mass coming out. Since we don't know the unknown mass of sodium nitrate, we have to solve for it using algebra. Next question. In 1828, Frederick Wohler produced urea when he heated a solution of ammonium cyanate. This reaction is represented by the balanced equation below. Ammonium cyanate yields urea. Explain why this balanced equation represents a conservation of atoms. Remember, in order to demonstrate conservation of atoms or conservation of mass, the amount of each atom present that we start with should equal the amount of atoms present that we end up with. So we have to count the number of atoms for each one of the elements present. Notice that there are 4 hydrogens on the left and 4 on the right. There are 2 nitrogens on the left and 2 nitrogens on the right, and each carbon and oxygen is also accounted for on the left and right side. So you could simply state that there are the same number of atoms of each element on both sides of the equation, or you could simply state no atoms are lost or gained in the chemical reaction, which would demonstrate conservation of atoms. Which equation shows conservation of atoms? Conservation of mass is illustrated when the number of atoms of each element present is equal on both sides. So which of these equations shows that? It has to be equation 3. There are 4 hydrogens present on the left, 4 on the right, 2 oxygens on the left, and 2 on the right because that coefficient is modifying that oxygen. Given the unbalanced equation showing the reactants and products of a reaction occurring at 298 Kelvin and 100 kilopascals, phosphorus solid plus molecular chlorine gas yields phosphorus trichloride liquid plus energy. Balance the equation below for the reaction using the smallest whole number coefficients. For problems asking you to apply conservation of atoms or conservation of mass, you must change the coefficient of the compounds in the chemical reaction so that the number of atoms on the left of each element equals the number of atoms on the right. So notice that there are 4 phosphorus here on the left. So that must mean we should add a 4 coefficient to the right side. And doing so will make the number of phosphoruses equal on both sides, but it changes the number of chlorines. If there's 4 present here, then that means that there are a total of 12 chlorines present. Well, 12 chlorines, when you start off with 2, means that we have to modify this by changing it to 6 to equal 12 chlorines. Now notice that everything is balanced. The number of phosphoruses on the left and right side is 4, and the number of chlorines on each side is 12. So remember, do not change the subscripts of any reactants or products in the reaction. You simply have to change the number in front, the coefficient. That's the only thing you're allowed to do when you apply conservation of atoms. And then you have to calculate what the correct coefficient must be in order to correctly balance the number of atoms. You can double check your answer simply by figuring out how many of each atom is present. Again, 4 phosphorus here, 4 here, 12 chlorines here, 12 chlorines here. Millions of tons of ammonia are produced each year for use as fertilizer to increase food production. Most of the hydrogen needed to produce ammonia comes from methane gas reacting with steam. This reaction, which occurs in a container under controlled conditions, is shown below in an unbalanced equation 1. You see the word unbalanced, chances are you're going to have to balance it at some point. The reaction that produces ammonia is represented by balanced equation 2, shown below. A catalyst can be used to increase the rate of reaction. A potential energy diagram for equation 2 is shown below. Oh, look at that. Balance equation 1 using the smallest whole number of coefficients. So again, what numbers do we need to add to this equation in order to ensure that the number of atoms of each of the reactants equals the number of atoms of products? Notice that the number of carbons is already equal, but the number of hydrogens is unequal. There are 6 on the left, 2 here, 4 here, and 3 here. So when we change the value, we know that all we have to do is simply multiply the number of hydrogens by 3 and everything else will be maintained. Notice that when we have this balanced equation, the number of carbons on the left and right side is equal to 1. The number of oxygens is also equal to 1, but the number of hydrogens is also equal to 6 because we have 4 here and 6 on the reactant side. And this 3 coefficient multiplied by 2 will also give us 6 hydrogens. The balanced equation below represents the reaction of glucose with oxygen at 298 Kelvin and 101.3 kilopascals. Determine the mass of carbon dioxide produced when 9 grams of glucose completely reacts with 9.6 grams of oxygen to produce 5.4 grams of water. You see that word completely reacts, that means that conservation of mass is present. So we have 9 grams of glucose reacting with 9.6 grams of oxygen to produce 5.4 grams of water. It's unknown how much mass of carbon dioxide is produced, so we're going to call that X. Applying conservation of mass will yield that the amount of carbon dioxide present has to be 13.2, because 13.2 plus 5.4 will be equal to 9 plus 9.6, which is about 18.6. So when we solve for carbon dioxide, we'll get 13.2 grams. Last problem. Many breads are made by adding yeast to dough, causing the dough to rise. Yeast is a type of microorganism that produces the catalyst zymase, which converts glucose to ethanol and carbon dioxide. The balanced equation for this reaction is shown below. Glucose plus zymase gives you 2-ethanol plus carbon dioxide. Determine the total mass of ethanol produced when 270 grams of glucose reacts completely to form ethanol and 132 grams of carbon dioxide. Remember, here our unknown is ethanol, but we do know that we start off with 270 grams of glucose. When we solve for the unknown, we know that 270 is equal to X plus 132. Therefore, X must be equal to 138 grams, or any value from 137.8 grams to 138.3 grams inclusive is possible. So remember, when it comes to conservation of mass, the mass in must be equal to the mass out. So if you are told that a reaction reacts completely, then that means whatever starting mass you have, or the sum of the starting masses, must equal to the sum of the products that you end up with. Alternatively, it might ask you to balance the equation, in which case you'll have to modify the coefficients in order to ensure that the amount of atoms, the number of atoms of each type of element is present. Sometimes the regents will ask you to justify why a particular equation shows conservation of mass, in which case you'll have to simply state that the number of atoms of each element on the left and right side that you start with and that you end up with is equal. Okay, I know that was a lot, but I appreciate your patience and thank you for watching.